Today's topic is decimal operation in smart contract, and it's DeFi-oriented use cases in ink. And today agenda is to is that this presentation is divided into actually several parts. At starting, we are addressing the problem of performing decimal operations. Then we want I will present the appropriate solution that is our library, and then we will go to the practical example using and we will discover constant product AMM in ink using our decimal library to show the advantages of using it, and the last part will be Q&A section. So before we dive into the technical details, let me share a few words about myself and the project I am representing. And I'm Wojciech, and I founded Invariant protocol, which is DEX, and the main scope of our solution and features related with that, and some features for future addressed is in most capital efficiency in the DeFi market specifically. And the project originates from the Solana, where it has deployed on mainnet since 2022, and since that gaining a decent amount of volume and TVL, but currently we are mostly focusing on building the invariant protocol on the Aleph0, and with the intention of launching our first testnet on Aleph0 soon. So okay, and now we can start from discussing clarifying floating points and fixed points numbers. What this exactly mean, and what exactly mean by decimal operation in this presentation. So, what is the distinguishing between these two types? We are here. You have some example of integer of floating points example that is that is built using two factors. The first factor is mantissa, and the second one is exponenta, and the result of this is basically the product of that. And below is presented the sign example of a byte word, and dividing it by sign, exponent, and mantissa, and each of these range, it has specific type encoded. And the second option is fixed point number, and here we always have the same precision. Basically, it's the integer number and the scale that which is to be honest, the metadata allowing us how to interpret this this value. Okay, so in the later stage, when I say the decimal value, I was mean a pair that is integer value and associated scale, and this scale allow us to interpreting the the value, the result. Yeah. Okay. So this is probably um, the main part of this. But before it, maybe there will be some question why we should use fixed point numbers and not floating points not numbers, and maybe there is some um, proposition from the audience about it, why there's recommended to use fixed point numbers over floating point numbers in smart contracts, especially in DeFi solution. Okay, so basically the main reason is that the behavior of floating points is non-deterministic, and which create issue with on the blockchain with synchronization at the state. So common example is when the blockchain not providing native support for floating point operation. There is some work around how to how to deal with it, and you can implement your self implementation of floating points. But in the DeFi oriented apps, developers not goes in this direction because there is other additional problems with that. Not only there's problem with deterministic operation, but there's problem with control over the precision of this of computational because when you design some protocols, you have the contract state where there is some reserve for tokens, and when transaction pass, you send some tokens and receive your tokens, and often you need to decide what about the roundings, and often you need to favor the contract balance that you rounding up the amount of token you receive and rounding down the amount of token you send. So in fixed point numbers, decimal numbers, there's option to control over your precision. And another issue is the gas optimization with operating with floating points. Yeah, and I think we could go to the overview. Yes, and now we are reaching the, let's say, the key part of this presentation, which I will present our solution, which is the library that supports decimal operation. Below is the QR code. You can scan it, and this is open source solution, so you can scan this code and go to the GitHub and check out this repository. Okay, and yeah, it's decimal library, and the main purpose is to automate multiple tasks and improve the security of your smart contract. Yeah, it's library that it's built using pure Rust, and it basically enable you to define your custom type support depending on your domain, but in DeFi first you often define some DeFi related struct like token amount, liquidity, price, or similar stuff. And the aim of this tool is to fully simplify the developer task related with. Okay, there's a question. Yeah, it supports now SDK in Rust. I will in next part I will talk about it more. Mm, uh, yeah, and mm, okay, I talk about simply some stuff and like many other libraries, and it's when if you are curious about how it's work, it's mainly built using macros that provide some generic templates, and thanks to that, it automatically generates your implementation for this type. Yeah, I think that the full potential of this library is shown in some DeFi solution. Okay, and here you probably use some standard libraries or some libraries from Substrate for the decimal operation. Maybe someone using uint library. And that library are open source and already battle tested. Um, so someone can ask the question why we introduce another tool, and the answer is this decimal library different from the mentioned previously, because we are the library on the higher level of abstraction. Like we are not implementing additional multiply operation manually. We use well-known battle tested and audited mathematical function, but we are our scope is around this typing and automating stuffs. And for example, let's say you have problem with handling overflowing or underflowing. Often, if you have two decimal numbers and you want to multiply this number, there's a risk of overflow of this result because the first argument have some scale, another also have some scale, and in intermediate operation there is possibility to overflow even if the result is inside your domain. So this library can automate your checking if overflow can occur, and it can automatically scale your integer underlying type to higher to make this operation, and after that back to the to underlying type. Yeah, another example is the converting between different types. In this library, it's easy to like operate with multiple types like multiple sum token amount by the fee, and then by the price, and divide by the token amount, because the scale of this operation will be as automatically calculated, so you don't need to care about this stuff. Okay. Okay. Maybe we can go go the genesis of this library, why we decided to create it, and basically we are building many different versions application, dApps, and we are handling large amount of boilerplate code that, like I mentioned, checking there is some overflow, or like mapping some error. Yeah, there's example in this code snippets that explaining pipeline. So on the left side is the some example of multiplying amount by the liquidity, with changing the scale and handling overflows and converting between types. And as you can see, there is many lines of code that there is only checking the errors. And on the right, it's a shorter version, and it used it's construct based on our apps. So here I define the type price, and also define the token amount type and liquidity. Okay, yeah, and so what does it look like in some practical product? And we are use this library not only to building on Ink, but as I mentioned, originate from Solana, and from start we are building everything, and talking everything. I mostly focus on map stuff using this library. These libraries are also used by some others Solana project, and this Invariant, the project is already on mainnet for over a year, and there's many millions of transactions, and the state is still correct. So yeah, that sign in practice case that this example should work. Yeah, and yeah, with some data we have about like 100K successful transaction per day, with 2 million daily USD volume. That's average data, and yeah, and this works properly, and this invariant code are also audited. Okay, so we can now go to the configuration parameters, and we provide extensive customization option. So, okay, what's the decoupling? Okay. Yeah. Okay, I should send the answer of this question. Okay, then back to the topic, the configuration parameters, and yeah, uh, if you want to define your own type, you have a few parameters here. Started with hash on this example, and the key parameter here is the underlying type, which represent the basic data type of stored value. So, for example, it can be U64 if you want, or U128 if you use some, for example, PSP 22 token. Yeah, the second one is scale, mm, a scale factor. It refers to the precision of the underlying types. So if I like choose the scale 5, that means this type the 5 5 decimal. So 10 10 to the 5 means you can interpret it as the one value. Okay, and the last one is extended type, and its specific type mm, it's specific for the case which the value uh, should be extended to the higher type to avoid some overflows that may occur in this operation. So you manually define your extended type in the definition. And it's also crucial what happens under the hood because yeah, as you can see, it's built using the macros, and what will happen with the macro was extended. This type become the regular Rust struct with the only one field, which is value, and everything that is related to it, it's not stored in metadata or on this type. Everything is like purely put inside the implementation generated by this library. So any metadata resists on this implementation, and that's is also advantageous to make easier with your, for example, custom serialization. Previously, I mentioned that it's blockchain agnostic solution. We use successfully it on the Solana, and we are also already like build our protocol on Aleph 0. It's open source. I will in next steps I will also send you the link for it. We are not on the testnet because we are handling some front-end stuff currently, but I think that's also good example of implementation with some advanced solution. Okay, and yeah, and how to add this library, and it's super easy. Like you can see, here's like other dependency you need to add it to cargo tom as your dependency, then mark your type as decimal, your struct, and provide your configuration, like I mentioned, underlying type, extended type, and decimal. If you want to store it as the ink storage inside the contract, there's also no problem to add ink storage macro to make it as the contract state. Okay, no, yeah, and you can now use it inside your contract in this massive implementation um or in storage or in some custom runtime. In the Rust, you don't need to use it only in the contract, so it also can be useful if you, for example, want to share some like your Rust code and your TypeScript code, because want to have the same result, you need make some simulation of performed transaction, so it also will be valuable. Okay, yeah, and now we can go to the practical example and this demo. I will be using the most famous primitives in the DeFi, which is constant product AMM. Yeah, most of you probably know this concept when you have X token and the Y token, and after each swap, the product of these tokens amount inside the pool reserves uh, stay constant. Okay, so just to remind you some example I present here. Um, Notation of how the state will be changed. It will be useful if I open the idea and you will be seeing some formulas here to compare. Okay, and here I use state transition notation. I don't know if you are familiar with this notation, but on the left you are the state before some interaction, and on the right you have state changed changed by this operation, and what exactly will be under the hood is this described below. Yeah, and there's no magic here. Here are add liquidity and remove liquidity, and basically it increase or decrease your reserve of your pool the, using proportion, like what proportion of your other token to reserve is added to the pool, you will receive the share of this liquidity represent uh, your position. Yeah, and in swap case, gives some manipulation with formulas, but you can mm, find it out just starting from this constant product and making some changes in formula. Mm, yeah, everything mm, it's based on the assumption that if you uh, mm, perform some swap, the product of X and Y tokens stays constant, assuming that the fee is zero. Okay, I think we can. Okay, now to go to the demo, and here is the QR code to this example that I will discuss now, and it will be valuable to send also this link on the chat. Okay. Yes, you pasted it. Okay. We go to the just the code. Okay. If someone can confirm that you can see my idea. There should be VS Code. Maybe I will zoom it in. Um, Yes. Okay, should be visible. Yeah, okay. So let's start from the configuration and from the cargo tom. And as you can see, there is the schema that looks similar to the basic flipper. The difference is that we added this decimal dependency. I already like downloaded it from GitHub repo and added it locally. Okay, and here we have the contract, and now here's important the type module. Okay, and yeah, maybe it will be good to start with this type definition. Okay, so here we use the decimal library, and I here started defining the base primitive that I will be used in this AMM. So basically, I need the token amount, and it will be the underlying type will be U128, and it comes from the standard that will described by PSP22 token. Okay, and as you can see, I use decimal 0, and I use extendable type, big type as U226. I also enable this primitive to be stored inside the contract using this derived macro that include ink storage. Okay, and as you can see, this struct is a bit different. And the difference is that it's the tuple struct, and you can choose choose if you want to use like tuple struct or this kind of struct with a single field that represent the values of token amount. Is example when I used just pure tuple struct. Another is liquidity with 2 decimals because we want to store some friction, extendable to U226. Price with similar configuration, but use different decimal, and it's 24 decimal, so it's example of type that we need high precision. Yeah, because price is in AMM represents the token ratio, yeah, and we need to high precision in this type because the only one possibility to change the price is by the swap change some perform some swap, and this swap will affect the changing the token ratio in pool reserve. And if you choose not sufficient precision here, you defining some minimal amount to perform the swap. So this price will no change, so the swap can be done. Yeah, so this is an example that we use type with high precision, and now we have percentage type, and it's U64 because we don't need a higher type with 6 decimal and extended type U128. Yeah, and the last one type is the ratio type, and it's also defined using alternative pattern which is tuple struct, and here we use U128 as underlying type, and with decimal type of 9. So that means 10 to the 9. You can interpret it as one value. Okay, yeah, and this configuration is mostly based on your needed. You should recognize which type require high precision and at some high decimal. Yeah, you can also calculate it quite easily. Like you have your underlying type and decimal. So when you know your domain, your maximum value and your precision, you can easily determine which underlying type you need here. Yeah, and this U226 type is also default type, which is extendable type. So if I remove this type, it will be assigned to the default type, and default type is the same as previous. Okay, yeah, and here is nothing special. We have entry points, like messages that represent some constructor. We have add liquidity, remove liquidity, swap, and some getters. So I think we can start from like constructor, and we basically create the empty pool. There is no X, Y, and consequently there is no liquidity. The only thing you are assigning is the percentage which represent the fee in this swap. Okay, yeah, and as you can see, I use these decimal types also as parameters in the message, as storage in smart contract, also is in calculation and in the return type. Yeah, okay. Okay, and as you can see, on liquidity, we are two cases here. Edge one is edge cases where I checked that liquidity is 0. It's already operation on yeah, as you can see, the liquidity type. Yeah, and it's edge case because you can't divide by 0, and here is example where all parameters is 0. So when there's the first deposit at liquidity inside the pool, we just reassign assign delta liquidity, the delta X token as X, and because the starting price is 1, we will assign also the same amount of Y token. And yeah, in all this implementation, I just skip the token transfer involving PSP22 because I want mostly focus on math stuff and how using these kind of type will facilitate many stuffs. Okay, and it's first example here. So we need to assign the liquidity, and the liquidity is product of X and Y. And here you have some example. Okay, you have X multiplied by y, and this is example of multiplication, but with prefix big, which means to force to extend the underlying type here to extend the type that we are defining in our configuration to this operation. Yeah, and after we have this product, we want to like change the type a product of tokens to instance of liquidity, and this functions from decimal is basically conversion between types. So we are passing product of the two tokens and receive the instance of the liquidity, and all magic that it's behind this this invocation is that it's automatically scale these values. So now we will return the instance of liquidity that has scaled as we defined here. It's probably 2. Yeah, and we can just assign it to the liquidity. Okay, and similar stuff from the decimal. It's the generic type to converting between between a different type of decimal that we are defined here. And now we want to calculate the ratio, and the ratio is this proportion that I mentioned in the presentation. It's delta x to the x, the amount. So it's what percentage of like you add to the you are currently adding to the already existing amount of x token inside this reserve. And yeah, as you remember probably, the delta x, and x is the type of the token amount, which their scale is 0. So now to calculating the ratio, the first steps is to extend the x to change to like create the instance of the ratio based on the delta x example, and after that divide this delta x to the x amount and returning the ratio. Yeah, and as you probably remember, this ratio has probably 9 decimal, because if you decide to choose lower, it will be generate more rounding problems. Okay, so, and as you remember on the previous formula, we now some alpha, and yeah, it's this ratio is ratio, and add 1 to this ratio to calculate our reserve state of x, y, and liquidity after that. And yeah, we are creating the instance of ratio, but now we are creating it from another type of function. It's from integer, so it's basically always return one value no matter about the scale you choose. And yeah, and now if you are instance of the ratio, created it, and the instance of the ratio created calculated based on the ratio delta x to x, you can easily add these two numbers, and now you have the alpha, and you are able to scale these values and assign new value for reserve and liquidity, as you can see also here. Because alpha has some pretty high scale, I here its multiplication, but with prefix big that I enforce to extend this type to avoid the overflow inside the intermediate operation. I will be receive the instance of the token X. So that's also fit in X type. Yeah, and it's also the suffix up, which mean you force to running this operation to up. Yeah, and it's example when you have some contract and you need to favor the reserve of the contract above the user. So if you add liquidity, you need to receive if you are rounding a bit more, one more. Yeah. Okay. Yeah, and the result type is the liquidity that the user add to this pool, and as you can see, it also it's calculated from completely different types, ratio, liquidity, and then it's also created based on converting the decimal type. Yeah, and the similar stuff is here in the remove liquidity. I also not like checking all of edge cases in this implementation. It's like a pure example, and there's similar stuff here. We are perform operation with the same combination of the types. Yeah, a bit different is in the swap example when we have our fee. So now we can, for example, create the percentage from integer 1. We are now create the stuff of percentage that contains 1, so it's mean 100%, and we can substrate fee to calculate like the amount of the token that have impact to this swap. And as you can see, there's also some prefixes with big type if you need to check the overflows, and suffixes to rounding the result up, and also some constructors that converting from one type to another. Yeah, and here is also some getters. You can also check how we return the price, and first we create the price one, and then we are operating with to calculate the current price that is defined by token ratio inside the these pools. But we are first create the price instance to force another calculation that using price decimal and also price extendable type. Yeah, and here are also some test cases that it's work correct. And if I maybe run this test, you can see you will see like the examples of tests here, but also examples of tests that will be generating after you defining these types. So if you defining your types, it will be automatically generate your implementation associated with your type that enables all these magic stuff. And also it will be generate automatically a test for for it, and yeah, it can be useful to finding some edge cases when you, for example, decide to choose like decimal 100 and the underlying value like U32, and that means, for example, you cannot create the instance of the one because the one is already overflowing your underlying type. Yeah, okay, so we are close to the end of this presentation. We will back to the presentation. Okay, yeah, here is the link to this report QR code. I also paste it in the chat, and yeah, that's it. Thanks for your attention. Here are 3 QR codes. On the left is our implementation of protocol, and it's a nice example of how these types behaves in some advanced example when you have like about 16 type or similar, how it it, in this kind of example you can see like full potential of this library. Yeah. On the right is the same QR code as here. It's the demo of this constant product IMM, the easiest primitives in our whole crypto, and in the middle is the Discord QR code, and you can join it, and if you can check this library, you can play with it, defining some types. Maybe, who knows, maybe it will fit well in your need to your contract, and you want to use this library. And if you have some question about the details how it works, so you can join this Discord and just ask the question. I'm definitely happy to discuss any details with this library. Yeah.